Start. Good morning. So yesterday we introduced the notion of the field, which is a physical entity which depends on space and time and describes some interesting physics. So now I would like to, and so we have seen that we can actually introduce the field when we discuss the vibrations of a string, and in that case the field was really the displacement of the string, and it depended on the time, but it also depended where on the string I am. And so that example was nice because you could actually get to the field theory from a discrete system, and so this is the case for most of the field theories. So anyway, so today I would like to discuss the field theory, which is really the cornerstone of modern physics. It has beautiful symmetries, it has beautiful history, and it has beautiful influence on modern physics. And that's the Maxwell's theory of electromagnetism. But before I do that, let me just make a very, very brief remark on what I mean by classical field theory. Of course, this will be an example of classical field theory. So classical field theory and so the idea of classical field theory is that before we had the field theory, we had the direct particle-particle interaction, right? That's an example of Newton's theory. So you have one body here, and it immediately, at an instant, influences the motion of the body here. So these bodies interact, and they interact at a distance. So the idea of the classical field theory is that an interaction at distance is not allowed, and instantaneous interactions are not allowed, rather that only local interactions should be possible. So then how do you explain the motion of our planets? Is that you say, well, one planet actually produces a field, and this field penetrates all of the space, and then this field interacts with the other body, again locally, there's no interaction at a distance, it's just local interaction, and that influences the motion of that body. So the idea is that matter does not interact directly one with another, directly through action at a distance, as Newton thought, but rather the interaction is local, interaction is local through this concept of the field via field. So one body produces the field and the other body interacts with this field. And so field is a physical quantity. Entity, I like that word better for the field. Physical entity at each point of space and time. So really the field is something which penetrates space, and this field it's a physical thing, and it's produced by this matter. Okay, so field is produced by matter sources, and this is according to field equations. So field equations are typically something which, if you know the distribution of the matter, you can determine how the field actually looks like in the space. Okay. But however, that's only one half of your theory, right? So given the distributions of the matter, I just find how the fields look like. To complete the theory, you also need to know, so given the distribution of the field, how does the matter actually evolve around? Okay, so that's the second part. So you also need equations of motion for the matter. Equations of motion for matter provided the field is already known. So in a given field, And so the classical field theory consists of two sets of equations, and it's the field equations, which, if I fix the sources, I know how the field looks like. And then also the second set of equations is the equations of motion. If I already know the field, then I know how the matter actually evolves. All right, so these are two sets of equations, and they are independent sets of equations. So typically, if you solve complicated problem, of course, you have to solve these things simultaneously, right? Because if I start moving the matter will start producing a new field, and so on. So this is actually, so typically you have to solve them simultaneously, and it's a complicated problem. However, you can do some approximations, and so typical approximation, which is done for the equations of motion, is that you consider test matter, meaning that the matter is really tiny, the charge is small, the mass is small, and whatever, and then you say, well, this tiny test particle really doesn't produce any fields, and if it doesn't really produce any fields, then I can just first solve the field equations given by the matter distributions of other bodies, and then I can consider the motion of a particle in this field, and so I can solve them first and then second. But that's only in the test particle approximation. Otherwise, you have to solve them simultaneously, and it's a very, very complicated problem. Okay? Are there any questions to this? So really, we have to have these two sets of equations. Okay? So now, the most familiar example to you is this Maxwell's theory here. And as I said, it consists of two sets of equations. We have the field equations, which were written down by Maxwell in 1860. And then we have the equations of motion for the matter, in our case for the test particle with charge E, and that's the Lorentz force law. And so this equation, oh no, and now it's dead completely. So this equation tells you if I fix E and B, there'll be the corresponding motion of my electron or whatever. And this equation tells me if I know the sources, the current J and the charge density rho, then I can solve for the fields E and B. Okay. So by the way, everybody has seen this notation. So I'll be using the notation. So if you have a function f and you put a nabla in front of it, what it stands for is just the gradient of f, right? So there's no sign in between, nothing. So now if you have a vector and you put a dot in between nabla and the vector, so this is just a divergence of v. And if you put times, that's the curl of v. So I'll be using this notation. I'll be also using the Laplace operator, which is just this thing here, or nabla square, and so on. You have also some beautiful vector identities which are satisfied, and so one of them is that the divergence of the curl is always equal to 0. So one identity is the divergence of curl equals to 0. And the other identity is that the curl of a gradient of any function equals to 0. There will be third identity which we'll be using, but basically these two are enough to tell you, to derive everything I'll be doing about the Maxwell equations. Are there any questions to the notation or anything else? All right, so this is completely broken. Okay, I will not touch it. It happened in the past that the whole thing actually fell down, so it's better not to really. Okay, so some remarks. So the first remark is, so by the way, most of these laws were already known before Maxwell, right? So certainly is the case for the Gauss law, for the Gauss's law, which is just these divergence equations. And the equation 3 is basically electrostatics. The equation 4 is that there are no magnetic monopoles. So the equation 2 was known. Well, not really, because people didn't really discover partial differential equations or didn't know how to write down partial differential equations. So Maxwell really put the experiments and whatever into the mathematical form. But if you look at this first equation here, then what was actually known is that curl of B should be something like 4 pi j, and the term minus d over dt was missing. Okay, and so that's called Maxwell's current or something like that. And Maxwell simply just put it into the equation without any experimental evidence so that the equations are more beautiful. Okay, and so why did he put it there is that there was another law which was completely independent to these equations, and that was the conservation of the charge. So the charge is conserved if you have some enclosed volume. The charge inside is conserved unless there is a current going outside of this volume. And the statement is that if you don't have the term, you don't have conservation of charge as a consequence of Maxwell equations. So in order to unify this thing, so Maxwell simply put that term there. Okay, so the first remark will be the charge conservation. Charge conservation. So once we have that term there, we can take a divergence of that equation number 1. So we are taking divergence of equation 1. And so then you'll be using these vector identities. So divergence of curl of B is identically 0. So we have 0, and then minus d over dt divergence of E. So I just swap partial derivative of t and partial derivative with respect to x. I can do that. And this is equal to 4 pi divergence of j. Okay. So now I can use the other equation. I can use the equation 3. And I know that the divergence of E is 4 pi rho. So let's think here is 4 pi rho. And so canceling 4 pi's and the minus sign, you're immediately getting the continuity equation for the current. That is d rho over dt plus divergence of j equals to 0. So that's the continuity equation. And what it means is the charge conservation. It implies conservation of charge. And of course, this is very simple. So first you have to say what charge is. So you say that charge is you integrate the charge density over some volume omega of dV. So I have some domain here, omega, and then there is some charge density inside. So I integrate this, and I get a total charge. And then you may be interested in how this charge evolved in time. And I'll put a minus sign just for convenience, dq over dt. So how is the total charge, the amount of total charge changing in the domain omega? And so this is minus d rho over dt dv. Now you can use this continuity equation. So minus d rho is just divergence of j. So it's an integral. This is still over omega. Omega divergence of j dv using the continuity equation. But now I can use the Stokes theorem or Gauss's theorem or something like that. Well, Stokes is the most it's the most general one, so let's call it Stokes theorem. And so you can just change this volume integral into the surface integral. And so this is beautiful. So if you write it in terms of differential forms, right? So you have integral over omega, and there's always one d somewhere. So there will be always one d on one side and then another d on the other side. So this is the Stokes theorem. So you have d on the left side, so you have to have d on the right side as well, right? So this is the volume integral, this is the surface integral, and there's a derivative on the left side, and there's no derivative on the right side. So we just kill this derivative here, and that's the integral over the surface of this domain. So that's d omega is just the surface capturing the domain, and is j times ds. Okay, and so what this is really is if you have the current flowing through that surface, through that boundary of omega, this is just the flux of that current through that d omega, which is current flux through the boundary through d omega. And of course, if there is no current flowing through the boundary, then the charge is conserved. Right? So that's what you mean by conservation of charge. So if no flux, then Q is conserved. And that's what you mean by conservation of charge. So people knew this, that the charge is conserved, right? So they knew this equation, basically. And so there were experiments to showing that. And of course, you can get it right way here only if you include this Maxwell's current. If you don't include this term, this term here, dE over dt, you just get the divergence J is equal to 0. And that's not the right thing you should be getting. So that's why, actually, this is what drove Maxwell to put that term there. All right. So now the second remark is about how many equations do we have. So can anybody tell me how many equations are here?
6, 8.
8, exactly. So we have 3 vector equations, which is 1 and 2, so 6. And then we have 2 scalar equations. So we have 8 equations. How many unknowns are here? 6. So the unknowns are E and B, right? So something is really, very strange, right? So we have 6 unknowns, which are E and B, both of them being 3-dimensional vectors. But we have 8 equations. So something must be wrong here, right? So something must be really, really fishy. And so how is this possible? Can anybody tell me?
I mean, we've used up one of the equations to relate rho and j, right? Like that's one equation worth of information that we've just doesn't relate the fields.
Okay, so there's some consistency condition the currents have to satisfy in order these equations to be compatible, right? So that's certainly true. Yes.
decompose the fields into planar waves, kind of find that the electric field and the magnetic field is perpendicular. So
that is true, but only in the absence of the sources, right? So you would have to. So the waves are typically if you don't have the sources, and so on. Okay, so probably you have heard this explanation, but basically the explanation is that the two scalar equations are not really the full equations, if you want. So they are sort of, instead of being like really the true evolution equations, they are initial conditions. And so the statement is that the two scalar equations are initial conditions for the other 6 equations. And so the way how to see this is that you can play with the first 2 equations. So proof is that let's take a divergence of 1. We have already done that over there. So we have, okay, let's start with divergence of 2. Sorry. Let's do divergence of 2 first. That's simpler. So we have divergence of curl is 0. And then plus d over dt divergence of b equals to 0. So that's one result. And then if you take divergence of 1, then divergence of curl again is 0. 0 minus d over dt divergence of E equals to 4 pi divergence of J. Okay, so now I will use that continuity equation sort of. So this is 4 pi d rho over dt with a minus sign. And so you can rewrite this equation as divergence of E plus minus 4 pi rho equals to 0, and then d over dt. Sorry, I'm saying something stupid. It's d over dt, divergence of E minus 4 pi rho equals to 0. This is what it is. So now if you look at these 2 equations which you just derived from the first 2 equations, is that precisely the other 2 equations, but now their time derivative, right? So basically the statement is if the equation 3 and 4 is valid at one instant of time, then the other 2 equations actually guarantee that they'll be valid all the time, right? In other words, if in the early universe after the Big Bang, I create the universe in such a way that I miss the magnetic monopole here, so that divergence B is equal to 0, then this equation here tells me that the divergence of B will be 0 always, right? And so there won't be any magnetic monopoles even now. Well, too bad for gut theories, which actually they predict magnetic monopoles, but nobody actually observed them so far. So if 3 and 4 satisfied in one instant of time, then satisfied always. And so in this sense, they form like initial conditions for the other 2 equations. By the way, from the evolution point of view, this is obvious, right? Because the only first 2 equations contain time derivatives. The other 2 equations don't. So if you look at these equations as evolution equations, then only the first two equations can be evolution equations, right? So there's many ways how to write these Maxwell equations. The way I chose here is that I put always differential operator acting on field equals to the source, right? And so that's the typical thing we should do in general relativity. You'll have some differential operator acting on the field equals to the energy momentum of the matter and stuff like that. So this is the relativistic version of the thing. Of course, if you were a mathematician studying evolution equations, you would always write dE over dt equals to something else, and dV over dt equals to something else, and that it would be obvious that there is no d over dt here. Okay. Are there any questions here?
But you use the continuity equation to prove that it's an initial condition, right?
Yes, yeah.
But
which sort of follows from that. So it is not like entirely true what I'm saying, but it's almost true, right? So certainly I could do this only if the current is conserved, right? So this would be true, certainly true, if I had an extra power telling me, yeah, the current has to be conserved.
Yes, if I take that as a postulate, right?
Yeah. So it's, yeah, there is a small caveat there. I agree with that. Very good. So but certainly what is true is that basically there's only 6 equations for 6 unknowns, and that's why this is a good system here. All right, so now Maxwell did write these equations. He wanted the current conservation, so that's why he included this d over dt term. But to his surprise, actually, this is a far-reaching consequences. And so let's call it Maxwell's triumph. And of course, that's the discovery of electromagnetic waves. So discovery of electromagnetic waves. So electromagnetic waves, so basically he discovered that even without the sources, even if I switch J and rho, I can still get interesting solutions. So for us, J will be 0 and rho will be 0, but still non-trivial solutions. So you are in empty space now, but you can still find interesting things. And these are the electromagnetic waves, which are disturbances of this electromagnetic field that propagate through your space-time. Okay, so how to show this? We'll use another identity here, and that identity is that curl of V is a gradient of divergence of V minus Laplace on V. Okay, that's another vector identity or differential identity, which is true. So now let us apply this identity, and let me start with the equation 2, and let's take curl of the equation 2. So then you have curl of E, curl of E, and that's gradient of divergence of E minus Laplace on E, just using this identity here, and plus d over dt curl of B equals to 0. All right. So now I can use the other equation. So now I don't have any sources. So divergence of E is equal to 0. So this thing is equal to 0. And curl of B from the equation number 1 is just dE over dt. So in other words, I'll just put a minus sign in front of everything, And so you have an equation that d square over dt square plus Laplace acting on E equals to 0. So your electric field satisfies the wave equation. So I'll call this operator box. And so you have an equation box on E equals to 0. And so you have the wave equation for your electric field. So now we started with Kel of 2. But if you do the same thing but Kel of 1, equation 1, you would discover that equally box on B equals to 0 as well. So both E and B satisfy the wave equation. So this is amazing because you know that actually wave equations do have solutions even in empty space, and so you just predicted that there must be electromagnetic waves. So there must be electromagnetic waves. But it's much better than that. You actually predicted that these waves have certain speed. And so the certain speed, so what if you had the speed here, then of course what would have to be here in order this to be dimensionally correct is that you would have to have c squared here, right? So only 1 minus, like this, you would have. So we predicted the speed, and they propagate at speed c in our units equals to 1. Okay, so it's amazing. So we predicted some universal speed, the absolute speed, which is given by Maxwell's theory. Okay, so now it has two consequences. One of the consequences is that people in 1860, they already measured what is the speed of propagation of light. Okay, and so they knew the speed. So Maxwell plugged in the things. Of course, he wasn't using these units. He was using some other units. But then he actually calculated the speed, and this speed precisely matched the speed of propagation of light. Okay, so this matched. So we predicted 1. It's perfect. This matches the speed of light. And then Maxwell said, well, okay, now I know what light is. It's just an electromagnetic wave. Okay? And so in this very instant, he basically unified the theory of light with the theory of electromagnetism. So really it was amazing, right? So there was a completely different theory for propagation of light, and there was a theory of electromagnetism. But because that theory of electromagnetism was missing this term dE over dt, people were not getting the wave equations for E and B. So they didn't know that there can be non-trivial solutions for E and B in the empty space. So there was no connection between light and electromagnetism. But now actually, just that light is just electromagnetic wave. Okay, that's first thing, which is like really, really amazing. And second thing, of course, the absolute speed c is incompatible with Newton's theory and with the standard Galilean transformations with Newtonian physics. So we know that in Newtonian physics the speeds are relative. So I can always add velocities and whatever. I cannot have an absolute speed, right? The absolute speed breaks the relativity of Newtonian mechanics. Okay, and so of course this immediately leads to special relativity, right? So from here it leads to special relativity. Well, it wasn't immediate. It took 45 years to realize this. And of course, from 1860, when these equations were formulated, to till 1905, where actually Einstein realized this, right? But Einstein was really, working with Maxwell equations, and he was asking, can I actually speed up so that I see the photons in front of me not going anywhere? Can I actually go to that speed? And then he realized I cannot. So there's this absolute speed which immediately breaks everything down in the old physics, and you get special relativity out of this. So I think this is like really, 1860 is the miraculous year where you unified light with electromagnetism, you unify the conservation of charge with the other Maxwell equations, and then basically you predicted special relativity. Yes?
How can I see that from these equations that this is the absolute speed?
Oh, no, I'm just saying. So this is in vacuum, right? There's no medium or anything. This is in vacuum.
Right.
Right? So I have these disturbances propagating in vacuum. And then I'm saying these disturbances actually propagate at the speed of light. Yes. Okay, there's some speed, some concrete value, which is predicted by the theory.
Why is it the highest limit?
I'm not saying it's the highest limit. I'm just saying the very existence of just absolute speed is incompatible with Newtonian things, because in Newtonian thing I can always add velocities and stuff like that. So no velocity is preferred to another velocity. Right? I can always move to a frame where I can achieve any velocity. So there cannot be any preferred velocity. But now I predicted a preferred velocity in empty space. Of course, in medium, as we've seen yesterday, we had the velocity v for the propagation of the disturbances in the string. But that's not in vacuum, right? That's some concrete medium. And in medium, yeah, you can have various speeds of propagation because it's just matter dependent and stuff like that. But here we are in vacuum. And so in vacuum, you cannot have absolute speed if the Newtonian mechanics is correct. All right. Other questions to this? Isn't this really amazing? So of course, Maxwell, after his great discoveries, went to Cambridge, and he drank himself to death, and never did any physics anymore. So,
Because of Cambridge or Maxwell.
all right. So we have done the discussion of these Maxwell equations in terms of the fields E and B. But it's also a very convenient tool to discuss it in terms of the potentials phi and A. Okay, so the potentials so in classical physics, the potentials are really just a mathematical convenience. So they just simplify these equations, and you can write down simplified equations instead of Maxwell equations. But in quantum physics, these potentials actually do play a role, and so they are the right fields to consider. And so you can actually test that they are physical. And one test is, for example, a Aharonov-Bohm effect, or whatever. So anyway, so let's just do this by mathematical convenience. So the statement is, I deleted the identities, which was stupid of me, but I can satisfy equation 4 automatically satisfied. So I had the identity that divergence of curl is equal to 0, right? So I had the identity divergence of curl of V is equal to 0 identically. So if I choose B to be a curl of some new potential A, then the equation 4 will be automatically satisfied. Okay, so now let's plug this to equation 2. So then I have curl of E, and then I have plus d over dt of B, but I'll just use this curl of A, and I know this is equal to 0. So I can group the terms. So I will have a curl of E plus dA over dt equals to 0. And then I had this other identity that curl of gradient of some function equals to 0. So this thing will be automatically satisfied if I set it equal to a gradient of some function. The convention is that you put minus, so minus gradient of some function phi, right? So in other words, I have this B here, and then I have E given by minus dA over dt minus gradient of phi. And if you do this, you just automatically satisfy the equations 4 and 2. So by the way, this thing is not unique, and you can show that there is a freedom in this description in terms of A and phi, A and phi, and it's called gauge freedom. Gauge degree of freedom and that's I can go from phi to phi minus derivative of any function of lambda, and I can go from A to A plus a gradient of that same function of lambda. And the statement is that leaves this transformation leaves E and B invariant. So of course I have curl, and then if I have curl of gradient, it's 0. So curl of A is the same thing as curl of A prime, and this thing, if I plug it here, you will find that the terms cancel, and you get the same E as well. Okay, so that's the gauge degree of freedom. So now this is amazing, right? So we actually transform from 6 variables, E and B, to 4 variables, phi and A. So this is a scalar, this is a vector. But moreover, this is actually, there is still some gauge degree of freedom. So actually, degrees of freedom in the Maxwell theory is definitely less than 4, right? As we shall see, actually, if you have no sources, you know that there are 2 polarizations of your electromagnetic waves. So in vacuum, or in other words, what I mean is the true degrees of freedom of the field, true degrees of freedom of field. So you don't need any, well, you don't have any sources, but the field still actually can have non-trivial solutions and whatever, and there are two independent things you can do with the field. We have 2 polarizations of the photon. And so the true degrees of freedom is actually 2. Okay. So now there's a beautiful way how to calculate degrees of freedom in gauge theories. And I think if you forget everything about this course, that's fine, but you should remember this theorem and this counting of degrees of freedom in gauge theories, because it will be very useful for later. And the statement is that if you have the gauge theory, and that gauge theory is described by some fields, you just calculate how many degrees of freedom are apparently hiding in that field. So in our case of electromagnetism, you have field A and you have field phi. So the apparent degrees of freedom are 4. And then you subtract twice the degree of freedom in your gauge function. So the gauge function is just 1 lambda, just one function, and you subtract 2 times that, and you get 2 degrees of freedom, which are the true degrees of freedom. So statement in any gauge theory we have the beautiful formula, the number of true degrees of freedom equals to the number of apparent degrees of freedom minus 2 times degrees of freedom of the gauge function. And so just remember this formula, meaning that basically the degree of freedom of the gauge function, each degree of freedom of the gauge function, you can use twice. Okay, so when you are gauge fixing, you should be killing 2 degrees of freedom. So for example, when we impose the Lorentz gauge, that's a scalar equation. It fixes only 1 degree of freedom. That means that the gauge is still not fixed completely. I can still impose another equation where I fix the gauge even more. Okay, so the example of electromagnetism is obvious. So Maxwell, we now have the fields which are phi and A are the fields, and they have 4 apparent degrees of freedom because it's simply 4 quantities. We have lambda, which is our gauge function, is the gauge function. Because it's a scalar function, it has 1 degree of freedom. And so then the true degrees of freedom, number of true degrees of freedom is simply 4 minus 2 times 1, which is 2, which is precisely, the 2 independent polarizations of the photon, or, the wave is propagating this way, right-handed or left-handed, whatever. So that's that. Of course, this works for any gauge theory. So example number 2 will be gravity. You don't know anything about gravity, but maybe you do. So you know that the gravity, well, you don't know. I'm telling you. The gravity is described by the metric. So G mu nu is the field. And that's 4 times 4 symmetric matrix. So how many components G mu nu has? So it's 4 times 4 symmetric matrix, but it's symmetric. So how many?
10.
10. That's 10 apparent degrees of freedom. So now we said, well, this is the gauge transformation which leaves Maxwell theory, Maxwell equations invariant. So similar degree of freedom is actually in Einstein's gravity. So we have gauge transformations which don't do anything. They basically just correspond to change of coordinates, and so you can go from the metric G mu nu to G mu nu plus doesn't matter what this is, nabla mu psi nabla nu psi mu. So there is some differential operator. It's in the same way as you have dt and nabla. So now we have this nabla mu index. But what is important is that this psi mu is a gauge function. Gauge function, and it is a vector. Okay, which is a vector. How many components the vector has? 4. So this has 4 degrees of freedom. And so then using this miraculous formula, so the number of true degrees of freedom is simply 10 minus 4 times 2, which is 2. So you just predicted that also in Einstein's gravity, we just have 2 independent polarizations of the gravitational waves. Or if you want, you can have 2 degrees of freedom for the graviton. Right? And so the counting works for other gauge theories as well. So when in string theory, you will consider these higher rank generalizations of Maxwell theory, like Karl Pramon fields and stuff like that, then the counting, of course, works as well. So just if nothing else out of this course, please remember this amazing formula here. Yes? Yeah? Katie?
How is this formula derived?
Very good. I'm not going to derive it at all. But so you can do it derive case. So I could do it probably case by case by really fixing the degrees of freedom. So going from the full Maxwell's theory from the full theory, and then fixing the gauge freedom one by one. See that this is what you get. This is best done in the Fourier space, and that's done in Zwiebach, for example. Maybe we shall do it at some point. However, the general proof, I think, can be found in this blue field theory book by Ramond and somebody, I think. So if you want to see the proof, it's in that book. Yes?
The fact that we have so many apparent degrees of freedom means that we're trying to describe the problem in a way that is more complicated than it should be?
Yeah, but that's exactly, that's the point of gauge theories. You are actually trying to you are overdoing it, right? So in order to describe 2 degrees of freedom, I'm actually using a matrix 4 by 4. But that's actually the biggest advantage of gauge theories. Because if you do this description here, although you have many degrees of freedom, you have nice symmetries. And you can exploit these symmetries. So precisely when we are talking about constraints, sometimes it's good to actually enlarge your phase space and get an extra symmetry. Right? So this is precisely what you are doing here. You are enlarging your description, you are enlarging your number of degrees of freedom, but you get some beautiful symmetries. And I would say that that's the biggest advantage of gauge theories. Like really, yeah. If you start, reducing everything down, if you start gauge fixing and reducing to 2 degrees of freedom, everything becomes suddenly really messy, and you don't. So you completely kill the symmetry of the theory, and then everything is like really, 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 really nasty. All right. So we have this. So we solved the equations 2 and 4. And of course, we still need to solve the equation 1 and 3. And this will lead to the wave equation for potentials. So what remains is to solve. So we introduce these potentials phi and a, and we solve identically equation 4 and 2. So we now have to solve 1 and 3. Okay, so let me start with equation 3. That's simpler, probably. So equation 3. So we just plug whatever we land, E and B are. So divergence of E. So we have divergence of E. But E is given by minus dA over dt, minus dA over dt, minus nabla phi, and that's equal to 4 pi rho. That's my equation 3. All right, so this is minus d over dt divergence of A. And then minus Laplace on phi. So pi rho. Oh, disaster. So I said that we have this gauge degree of freedom, but actually I didn't tell you about very nice particular choice of the gauge. And that gauge we will exactly need here. So using the freedom, using the freedom, the gauge freedom, the gauge freedom, we can impose the gauge, impose the gauge, which is called Lorentz gauge. So by the way, big confusion. There's two guys, Lorentz and Lorentz, with T and without T. So the guy who is famous for the force here is with T. And I think the guy who is famous for this choice of the gauge is actually without T. So big confusion. Okay, so the statement is I can use that freedom of choosing lambda so that we have this nice gauge, and that's divergence of E, divergence of A plus dt phi equals to 0. Okay, so the statement is you can always find such a lambda so that this thing will be true. Okay. That's Lorentz gauge. This is true no matter whether I have sources or not, whether I have currents and charge density. Statement is if you don't have currents and charge density, this doesn't fix the gauge completely, and you can still reduce the number of true degrees of freedom by 1. So this is just a scalar equation. So reducing the number of degrees of freedom by 1, but that's not enough. I have to reduce one more, and so you can still fix the gauge more if you don't have sources. Okay, okay, let's use this Lorentz gauge here. And if I do it, I can just replace divergence of E with minus dt phi. And so then what you are getting is d square over dt square of phi minus Laplace on phi is 4 pi rho, or box on phi is equal to minus 4 pi rho. So the equation 3 leads to the wave equation for phi with some non-trivial source rho. So finally, the equation 1. So the equation 1 is curl of B. Okay, so curl of B, B is curl of A, minus d over dt, minus d over dt, E is minus dA over dt minus nabla on phi, and that's equal to 4 pi j. So now again we have to use that stupid identity of curl, which is the gradient of the divergence. This thing is a gradient of divergence of A minus Laplace on A, so that's the same identity again. And then we have this thing here. So then you are seeing that we have the term d square A over dt square minus Laplace on A. So that's this term here plus that term here. And then we have plus gradient of divergence of A, that's this term here. And then minus d phi plus d phi over dt equals to 4 pi j. So whatever stands here inside the gradient is again the Lorentz gauge condition. So this is 0 by the Lorentz gauge condition. And then we are getting exactly the same wave equation now for the vector potential A, which is now minus 4 pi j. Okay, so in terms of the potentials, the Maxwell equations are actually really simple. They are basically like wave equations with some sources on the right-hand side. Right? So I kill two equations by simply introducing these potentials A and phi. That's really mathematically convenient. So now I have only 4 quantities instead of 6. And then moreover, these 4 quantities actually satisfy nice wave equations. Questions? All right. So now what we would like to do is that we would like to find a general solution of these things. Okay. So, of course, these are linear equations. And so you have some differential operator acting on phi equals to non-trivial right-hand side. And the general solution is, well, I can have a solution of the homogeneous equation where the right-hand side is 0. So I will take the most general solution of the homogeneous equation plus a special solution which solves the right-hand side. Right? And that's the most general solution of these equations. So solution equals to solution of homogeneous equation plus a special solution solving this equation on this right-hand side. Of course, the solution of the homogeneous equation, box on phi equals to 0, is a wave, right? So I can have any waves propagating in my space-time. So this is basically waves. And then I can have the special solutions which correspond to my sources here. So now what I will concentrate on is to find this special solution. And we will do it by the method of Green's functions. So that's a very convenient method for finding these special solutions with non-trivial right-hand side. Are there any questions before we start doing this? We still have 10 minutes, so let's see how far we can get. Yeah?
This counting of true degrees of freedom, it is just in the classical field theory?
Oh, it'll be true in quantum as well.
But it's not the same counting. Like when you are analyzing, for example, a renormalization flow, you can obtain more operators that have more degrees of freedom.
I see. No, but here I'm talking about the free field without any, well, there's no self-interactions like that. There's no loops.
Okay.
So this is just free field. I think that's correct. So still true in field theory, quantum field theory, that you will have like two independent polarizations of the photon. Still true. 2 spins of. I hope this is correct statement, maybe. So anyway, so what we're trying to find is to find the special solution. Use the method of Green's functions Okay, so what we want to try is to find a Green function G which depends on R prime, T, and T prime. So I'm interested in, I have some source situated at, I don't know, R and T, and then I'm interested how this thing sort of propagates to R prime and T prime. However, from the homogeneity, so I can translate things, I can use the isotropy of the space and so on. so from the isotropy, you can show that the green function actually has to be function. So these are vectors of r minus r prime from the isotropy. And then from the time translation invariance, I can show that it will also be a difference between the times. It will be function of t minus t prime. Okay, so this is isotropy plus time translation invariance. So the green function will be function only of the difference between whatever I study, where I start to where I propagate, and then whatever the initial time is. So now let me call these quantities R and capital T. And so this is a vector R, because these are vectors, and then that's just the difference between times. So then the statement is the green function is solving the same equation, but now with the right-hand side replaced by the corresponding delta distribution source. Okay, so now you know everything about distributions from Dan's course. It's perfect. So what we will be imposing is that box on G, which is a function of R and T, is, and then I'll put a minus sign. This is just a convention, delta T. Okay, so I'm just replacing the right-hand side, which was, I don't know, 4 pi rho, with just the delta source here. And then the statement is, if I can solve this equation here, I can find G so that this is true, then the potential phi, which is a function of R and T, is simply given by the integral of G R R prime T T prime, which however has this special form, and then 4 pi rho dr prime dt prime. Okay, so this is the special solution which I'm after, which will be solving my equation box on phi is minus 5.
Sorry, show me
4 pi rho.
the minus sign.
I think, well, let's see. So let's verify that this is the right thing. Probably it's not. Maybe.
Boundaries here, right?
So now what you have to do is that to check. So box on phi. Well, box acts only on R and T. So it doesn't. Okay. I'm too hasty. So 4 pi rho R prime T prime dr prime dt prime, right? So this is what it is. So the statement is, if I can find a solution of the green function, this green function here satisfying this equation, then you will find the solution in this form. So let's check that it satisfies the equation we want to satisfy. That is, box on phi is equal to minus 4 pi rho. So box on phi, but box is a derivative with respect to R and with respect to T. So the only thing which depends on R and T is this G here, because this is a function of R prime, T prime, and I'm integrating over R prime and T prime. And so I can pull this box through the integration. So this is equal to an integral on box on G, and then 4 pi rho, and whatever dr prime dt prime. But the statement is that box on G is, by this definition, just minus delta R minus R prime. So this is minus delta R minus R prime, delta T minus T prime. And so now I can use these deltas to kill the integration. So simply the integral over T prime just changes T prime everywhere to T. And the integral over R prime changes R prime to R. And so this is simply minus 4 pi rho R and T. Right? So this is the proof that that's the right thing to do. So I've chosen a sign to be minus here so that I have that minus there nicely. Okay. So the statement is, if I can find such a function which satisfies this equation here, then my special solution is simply given by integral over that function. All right.
Why would to have boundary conditions?
Oh, you could have some boundary conditions, and then you would have to impose some more restrictions on your Green's function. Here I'm just pretending I am in the overall infinite space-time, and so I don't care about the boundary conditions. But yeah, you could treat it maybe. Well, but you have here the wave equation, so I don't know what about the boundary. I don't know. Yeah. So let's just ignore the boundary things here. In fact, actually, boundary things are very important, as we shall see later on. But let's ignore the problem for now. So I have 3 minutes, so let's just do it in the k-space, right? So let's take that equation and let's do the Fourier transformation on your function g. And so let's find how the g function looks in the Fourier space. So what I do is that I take g t and then Fourier transform it in everything, 2 pi to the power 4, and then you will have an integral over k, an integral over omega, and then you will have the Fourier transform of that function, which I call g k omega, and then just the exponential ei k times r minus I omega t. Everybody's seen Fourier transform. Anybody not seen the Fourier transform? Okay, so then this is simple. Very good. So now what you want to do is that you want to apply box on this, right? So you want to apply box here. And so this is just an integral over k and omega. This depends on k and omega. So the only place where the box can act is the exponential, right? And so the box is just a derivative with respect to t twice and derivative with respect to r twice. So what this is 1 over 2 pi to the power 4, and then an integral dk integral d omega, and then g, k, and omega. And so if I differentiate with respect to time twice, I get, for each of them, I get omega, so I'll have omega square. And similarly, I'll have k square here. The i's really don't matter. Well, they do. But also, I have this strange sign for the box operator, right? So the box operator has some important minus sign in front of the time direction, and then plus Laplace, which is the spatial direction. So there's different signs. Okay, so then if you put everything together, just omega square minus k vector square. So this is when I act with box on g, written in terms of the, and then of course I have the exponential still, e to I k times r minus I omega t. So now I require that this is equal to minus delta r delta t. And then now you just write down the Fourier representation of your delta function. And so this is just minus 1 over 2 pi to the power 4 has covered the Fourier representation of the delta function already. He did, perfect. So then this is just dk and d omega, and it's just this exponential. Okay, so this is what we require this to be true. Of course, now I can put the integrals, the left-hand side integral is the right-hand side integral, and I can compare, and I see that g times this thing has to be equal to minus 1. Okay, and so I conclude that my Green's function in the k and omega space simply looks like 1 over k vector square minus omega square. And so that's perfect. So now we have the solution for the Green's function. unfortunately, the solution at this point is in this Fourier space, in the k and omega space. So what we will do next time is that we will actually do the painful thing, and so our G in the R space, R and T space, is given by this integral here. So we will just take this guy here, plug it here, and do the integration to find what G is in the real space. Once we have G, we have the solution given by here. That's the special solution, and my solution of the wave equation is a most general solution of the homogeneous equation plus this special solution, and then we will be done with the Maxwell's theory. Okay, so let's do it next time. Questions? All right. See you tomorrow.